Let's explore how shared neutral circuits can lead to energy savings, focusing on the reduction of cable heating. This explanation provides the calculations and reasoning behind these savings. First, let's consider a calculation for 8 50-foot 12-gauge conductors, determining what it would take to equal a 60 watts I²R loss. Step 1 involves calculating the total resistance of the conductors. With 8 50-foot lengths of 12-gauge wire, we multiply 8 times 50 feet, then multiply that result by the resistance of 12-gauge wire, which is 1.7 ohms per 1,000 feet. This gives us a total resistance of 6.8 ohms. Step 2 involves using the power formula I²R equals watts to determine the current required to produce 60 watts of heat loss across this resistance. Rearranging the formula to solve for current, we get I equals the square root of watts divided by resistance. Plugging in the values, we get I equals the square root of 60 watts divided by 0.68 ohms, which equals the square root of 88.2. This results in a current of 9.4 amps. Therefore, if the above is correct, the heating is 100 watts at 12.1 amps and 150 watts at 14.85 amps. In the 60 watts case, the above translates into a significant energy savings, 60 watts on an 1134 watt circuit or 5%. Question 1. The energy used heating cables is 60 watts when the circuits carry 9.4 amps. This statement is correct. The energy used to heat the cables is equal to the I²R losses in the cables. The I²R losses can be calculated using the formula P equals I²R, where P is power in watts, I is current in amps, and R is resistance in ohms. Question 2. Assumption of 12 American wire gauge wire at 0.85 power factor. Simple DC resistance formula conveniently. Table 9 gives 1.7 ohms per 1,000 feet. The assumption of 12 American wire gauge wire at 0.85 power factor is reasonable for a typical branch circuit. The simple DC resistance formula R equals ρ L over R can be used to calculate the resistance of the wire, where ρ is the resistivity of the wire material, 17.24 micro-ohm centimeters for copper, L is the length of the wire, and is the cross-sectional area of the wire. Question 3. Assumption that cables heating in the wall will be reflected at customer's electric meter. This assumption is valid for the purposes of calculating the energy savings. The energy used to heat the cables will be reflected in the customer's electric bill as increased electricity consumption. Question 4. Drawings used to show the options. Drawings of the different wiring options can be helpful for visualizing the differences and understanding the energy savings that can be achieved. Question 5. A better statement, easier to remember or more useful or accurate, whatever. A better statement that is easier to remember, more useful, and more accurate could be by using a shared neutral for multiple branch circuits. You can reduce the total energy used to heat the cables, resulting in energy savings of up to 5%. This statement is clear and concise, and it accurately describes the energy savings that can be achieved by using a shared neutral. Considering an 1134 watt circuit operating at 120 volts, the current draw is approximately 9.45 amps. A 60 watts reduction due to minimized cable heating represents a notable energy saving. The heat generated in electrical conductors is a direct result of the current flowing through them and the resistance of the wire, described by the formula P equals I²R. In typical wiring scenarios, conductors are bundled together. This proximity can lead to heat buildup due to reduced heat dissipation. Multi-wire branch circuits, or MWBCs, which share a neutral conductor, can potentially reduce the overall current flow in the neutral conductor, thereby reducing heat generation. The amount of heat generated is proportional to the square of the current, so even small reductions in current can lead to noticeable reductions in heat. The actual savings achieved by using a shared neutral depend on the specific load balance between the circuit sharing the neutral. If the loads are perfectly balanced, the neutral current is theoretically zero, resulting in the greatest reduction in heat generation. However, in real-world scenarios, loads are rarely perfectly balanced, so the savings will be less than the theoretical maximum. While a 5% energy saving may seem modest, it can accumulate over time, especially in large buildings with numerous branch circuits. Furthermore, reducing heat generation in electrical conductors can also improve safety by reducing the risk of overheating and potential fire hazards. Factors such as conductor size, insulation type, and ambient temperature also affect the heat dissipation and overall energy efficiency of electrical circuits. It's important to consider these factors when designing and installing electrical systems to maximize energy savings and ensure safety. To further clarify, let's delve deeper into the concepts and calculations involved. The key principle at play here is the reduction of current in the neutral conductor when using a shared neutral configuration in a multi-wire branch circuit. In a standard circuit with two ungrounded conductors and a neutral, each ungrounded conductor carries current to its respective load, and the neutral conductor carries the imbalance of current back to the source. However, in an MWBC with a shared neutral, the neutral conductor only carries the difference in current between the ungrounded conductors. If the loads on the ungrounded conductors are equal, the neutral current is zero. The formula for calculating the neutral current in an MWBC is a neutral equals absolute value of Ione minus HV, where neutral is the current in the neutral conductor, Ione is the current in the first ungrounded conductor, and HV is the current in the second ungrounded conductor. This reduction in neutral current directly translates to a reduction in I2R losses in the neutral conductor, as the power dissipated is proportional to the square of the current. For example, if each ungrounded conductor carries 10 amps and the loads are balanced, the neutral current is zero, and there are no I2R losses in the neutral conductor. However, if one ungrounded conductor carries 10 amps and the other carries 5 amps, the neutral current is 5 amps, and there will be I2R losses in the neutral conductor, but less than if each circuit has its own neutral conductor carrying 10 or 5 amps. The resistance of the conductors also plays a significant role in determining the magnitude of the I2R losses. Conductors with lower resistance will have lower I2R losses for the same amount of current. This is why larger conductors are often used in high current applications to minimize energy losses and prevent overheating. The type of conductor material also affects the resistance, with copper generally having lower resistance than aluminum for the same size conductor. In addition to reducing I2R losses, shared neutral configurations can also reduce the amount of copper required for wiring, as one neutral conductor can serve multiple circuits. This can lead to cost savings and reduced material consumption. However, it's important to note that shared neutral configurations must be properly designed and installed to ensure safety. Overloading the neutral conductor can lead to overheating and potential fire hazards. It's also important to ensure that the neutral conductor is properly sized to carry the maximum potential imbalance of current. Local electrical codes and regulations should be followed when designing and installing shared neutral configurations. Considering a practical example, suppose a commercial building has 20 branch circuits, each serving a lighting load of 5 amps. If each circuit has its own neutral conductor, there will be 20 neutral conductors, each carrying up to 5 amps. However, if the circuits are arranged as MWBCs with shared neutrals, the number of neutral conductors can be reduced, and the current in each neutral conductor will be lower, depending on the load balance. This can lead to significant energy savings and reduced material costs. Furthermore, the reduced heat generation in the conductors can also improve the lifespan of the wiring and reduce maintenance costs. It is very important to understand the limitations and potential drawbacks of shared neutral configurations. Firstly, if the neutral conductor is inadvertently opened or disconnected, the voltage on the ungrounded conductors can become unbalanced, potentially damaging equipment connected to the circuits. This is known as a floating neutral condition. Secondly, shared neutral configurations can be more complex to troubleshoot than standard circuits, as a fault in one circuit can affect multiple circuits sharing the same neutral. Thirdly, shared neutral configurations may not be suitable for all types of loads. For example, circuits serving sensitive electronic equipment may require dedicated neutral conductors to minimize noise and interference. In addition to the points discussed earlier, it's also important to consider the impact of harmonics on shared neutral circuits. Harmonics are distortions in the sinusoidal waveform of alternating current, which can be caused by nonlinear loads such as electronic devices, fluorescent lighting, and variable frequency drives. Harmonics can cause increased current flow in the neutral conductor, even when the loads are balanced. In particular, tripling harmonics, which are odd multiples of the third harmonic frequency, such as third, ninth, and 15th harmonics, add directly in the neutral conductor in the three-phase system. This can lead to overheating and potential damage to the neutral conductor. To mitigate the effects of harmonics, it's important to use appropriate filtering techniques and to ensure that the neutral conductor is sized to handle the increased current. It's also important to consider the use of dedicated neutral conductors for circuits serving nonlinear loads. The National Electrical Code, or NEC, provides guidance on the sizing of neutral conductors in circuits with harmonic currents. NEC Section 220.61 provides requirements for calculating the neutral load in a three-phase system, taking into account the presence of harmonic currents. In general, the neutral conductor should be sized to carry the maximum unbalanced load, plus any additional current due to harmonics. Furthermore, it's important to consider the impact of voltage drop on shared neutral circuits. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of electrical systems. To minimize voltage drop, it's important to use conductors of sufficient size and to keep the length of the conductors as short as possible. The NEC provides guidelines for calculating voltage drop in branch circuits and feeders. NEC Section 210.19a provides requirements for the minimum size of branch circuit conductors taking into account voltage drop. It's also important to consider the impact of ambient temperature on the ampacity of conductors. Ampacity is the current carrying capacity of a conductor. The ampacity of a conductor decreases as the ambient temperature increases. This is because the conductor's insulation can degrade at higher temperatures, reducing its ability to safely carry current. The NEC provides tables that list the ampacity of conductors at various ambient temperatures. NEC Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 2000 volts based on conductor size, insulation type, and ambient temperature. When conductors are installed in raceways or cable trays, the ampacity must be derated to account for the increased heat buildup. The NEC provides adjustment factors for derating the ampacity of conductors in these situations. NEC Section 310.15c provides adjustment factors for more than 3 current-carrying conductors in a raceway or cable tray. These adjustment factors reduce the allowable ampacity of the conductors to prevent overheating. In addition to the technical aspects of shared neutral circuits, it's also important to consider the economic aspects. While shared neutral circuits can lead to energy savings and reduce material costs, they may also require additional labor and engineering costs. It's important to perform a cost-benefit analysis to determine whether shared neutral circuits are the most economical option for a particular application. The cost-benefit analysis should take into account the initial costs of materials and labor, as well as the long-term costs of energy consumption and maintenance. It's also important to consider the potential for increased safety and reliability when evaluating the economic benefits of shared neutral circuits. In summary, shared neutral circuits can offer significant energy savings and reduce material costs, but they must be properly designed and installed to ensure safety and reliability. It's important to consider the impact of harmonics, voltage drop, and ambient temperature when designing shared neutral circuits. It's also important to perform a cost-benefit analysis to determine whether shared neutral circuits are the most economical option for a particular application. Always consult with a qualified electrical engineer or contractor when designing and installing electrical systems. They can help ensure that the system is safe, efficient, and compliant with all applicable codes and regulations. Furthermore, regular maintenance and inspection of electrical systems are essential to ensure their continued safety and reliability. This includes checking for loose connections, damaged insulation, and other potential hazards. By following these guidelines, you can maximize the benefits of shared neutral circuits and ensure the safety and efficiency of your electrical systems. Remember, electricity is a powerful force that must be treated with respect. Always follow safe work practices and consult with qualified professionals when working with electrical systems. The discussion of shared neutrals and their potential energy savings leads to a broader consideration of energy efficiency in electrical systems. There are numerous strategies and technologies available to reduce energy consumption and improve the overall efficiency of electrical systems. These include using energy-efficient lighting, installing variable frequency drives on motors, optimizing power factor, and implementing energy management systems. Energy-efficient lighting, such as LED lighting, can significantly reduce energy consumption compared to traditional incandescent or fluorescent lighting. LED lighting is more efficient, longer-lasting, and produces less heat. Variable frequency drives, or VFDs, can be used to control the speed of motors, allowing them to operate at their most efficient point. The VFD can also reduce energy consumption by reducing the starting current of motors. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted. Power factor correction can be achieved by installing capacitors in the electrical system. Energy management systems can be used to monitor and control energy consumption throughout the building or facility. These systems can provide valuable data on energy usage and can be used to identify areas where energy can be saved. In addition to these strategies, there are also a number of government incentives and programs available to encourage energy efficiency. These incentives can help offset the cost of implementing energy-efficient technologies. The Environmental Protection Agency, or EPA, offers a number of resources and programs to promote energy efficiency. The Energy Star program is a voluntary labeling program that identifies energy-efficient products. By implementing these strategies and taking advantage of available resources, it is possible to significantly reduce energy consumption and improve the overall efficiency of electrical systems. This not only saves money but also reduces the environmental impact of electricity generation.